can be presented in a GIS format. So that's one of the things that we're looking at in the future. What are the different options for display of this kind of information? Thank you. Yes.
So, in terms of evaluating the human capital, economic capital, and the natural capital, you have to place value on those things. And, are there some common denominators that are used, like, the cost of things?
Well,
or a thermodynamic denominator, the energy required, or?
there have been a number of efforts to try to find what we call a common numeraire for environmental, social, and natural capital. And it is challenging. Economists have tried to come up with methods for valuing natural capital, for example, ecosystem service valuation. Also for valuing human capital, and there are ways to do that. Industry is very interested in this, valuing what they call intangibles. We have also used energetic methods. You mentioned thermodynamics. So we've used exergy type of metrics. My colleague, Dr. Bhavik Bakshi, who you may have heard of, is a leader in this field. So that allows us to combine these dissimilar kinds of impacts in some common scale. However, we have not tried to do that with this particular model. In this case, we have kept all the indicators separate. We've not tried to come up with a common accounting scheme. That could be done as a sort of a post-analytic layer on top of this.
So then when you do that, if you don't take that into account, then does your system, basically really depend on people's perceptions of?
Well, then you get into the question of trade-offs. Okay, so I know it's going to cost me X dollars, and I'm going to maybe improve tourism by X percent. But I may still have some hypoxic zones. So you have all these outcomes that you need to trade off. And there was a whole class of methods in decision theory and decision sciences that help people to deal with those trade-offs. Once again, we did not include that in this model. We know we could do that. Right now, we're just trying to capture the fundamental physical, economic, and social indicators.
Thank you, Joseph.
Thank you.
Our next session was organized by Gene Whalen and Bruce Hamilton, and I'll let them come up and take over.
Yes, my name is Gene Whalen. I'm a researcher with the Office of Research and Development for the U.S. Environmental Protection Agency. The next session deals with national and international integrated environmental modeling activities. We have 3 speakers. And the first is Peter Hirschberg, who is a senior hydrologist and water systems integrator. He works for Deltaris USA Incorporated. Excuse me. He has a PhD and master's degree in civil engineering. He develops strategic and operational decision support systems as well as interoperability standards for integrated water resources management issues. And he also leads the development team of the Open Modeling Interface Association. We call it OpenMI, which is a software standard for coupling environmental modeling components at runtime. And he's been kind enough to provide us with a report out of the recently completed International Integrated Environmental Modeling Summit that we held in the USGS headquarters in Reston, Virginia, hosted by Pierre Glynn, and which was held in December. Peter?
Thank you, Gene, for introducing me. I'm working at Deltaris, which is a research institute based in the Netherlands with a little office in Silver Spring here in Maryland. And they are a research institute in they call it delta technology nowadays. Being able to live in a delta with all the issues of coastal water, land subsidence, soft soil, including all the pollution you get there because of all the upstream activities. The presentation I'm going to give is basically a roadmap which was created out of this summit which we held last year in Reston, where all those different organizations on this slide were there. A bunch from Europe, mostly of them, they were more or less organized in the OpenMI Association, and the whole group of US representatives. And that vision that is, and the roadmap is basically organized around 4 domains of integrated environmental modeling. The area of applications, the science, the technology, and the community of practice you need to make it all move forward. And I'm going to address those different aspects first from, okay, what is actually their characteristics, what are their challenges, and how can we move forward to making it better. The applications, integrated environmental modeling applications, they are there to actually help us in organizing all the information needed to make decisions. And as you all know, it's to a large extent all about integrating all those different compartments in the environmental system, plus the economic system and the societal system, the legal system. All those different components have to come together. And there's information there which you need to communicate to a wide range of stakeholders. To get there, we need a holistic approach, as very nicely illustrated in the previous lecture. And one of the challenges we have there is for the few applications which we have, to make them more reusable, make them more accessible, and to take care that they can adapt with the questions which evolve over time. Each time there's new societal problems which have to be addressed, and if you have a static system which cannot evolve with it, then after a while it's useless, it doesn't help anymore. And what's also lacking is really good documentation of the best practices and examples you can use in education and training, because the applications itself, the multidisciplinarity of it, the transdisciplinarity of it, that's really a big challenge. The science is there to help us underpin all the applications we develop. And a big challenge there is especially the disciplinary diversity which is out there. I remember last year when Pierre was showing us his lab, a bunch of us Europeans. Then I realized that when he talks about modeling and I talk about modeling, that we even have different models in mind. So even the word model is not shared in the same way among the various disciplines. So let alone all the other aspects which are out there, which need to be integrated. And the key challenge of the science of integrated environmental modeling is that you know how to integrate to overcome that diversity. And when you know how to overcome the diversity, you can also synthesize the results to the specific stakeholders and translate it in the way they would like to have that information, the way they understand that information. And so a big challenge is to get that diversity in place, and to do that we use those conceptual models, but we have to link them to to the problems and to the quantitative system. And a lot of our science aspects are actually related to a picture which came up in that workshop about interoperability, that you are able to exchange on the conceptual level the same kind of knowledge and ideas and information, which is quite different than the technical interoperability, which also is needed. Of course, there's the traditional challenge of dealing with all the data, getting it organized in a coherent way, dealing with either too much data, where you have to find your way, or too little data, and those things will always stay as it looks like. The technology is there to take care that the science we have, that we can make it usable, apply it. And a key aspect of the technology is to create the linkages, the exchange capabilities for the different components, and to facilitate that we can collect the data and that we, with not too much effort, can prepare it for putting it into the quantitative models we have. Of course, we have to also manage the execution of those models, and we have to have the user interfaces such that we can interact with it, that we can really exchange the information. The challenges are much more in the technical level and the syntactic level of interoperability. It starts with non-standardized file formats to programming language incompatibilities and model classification. That are you talking about linking an evapotranspiration model at that kind of level, or are you more talking about connecting a whole soil moisture accumulation model to another model? There's different levels of what you can address, and there is some way to go there still. And one of the main things for both the commercial as well as the federal and the state regulators is how sustainable is that model? How is there someone behind it who's backing it, or is it something which is created at the university, is put out on the open source, but nobody takes care of it anymore? So is it still a reliable entity to build upon? And even now, in my presentation, I nearly would neglect the fact that we do not document our models properly enough with the metadata. I was nearly at the next slide. I thought maybe I should say that thing, because that is, it's very common. You develop, you're just in time to deliver the result, but you don't have budget or you don't have time anymore to properly document your model and to make it such that it is reusable. And then the fourth dimension which was addressed is the community, which should provide a societal context, and which that discipline which has to address those diversities can evolve. And a key aspect is, of course, the transdisciplinarity, the fact that there should be a wide range of stakeholders there. Academic, commercial, federal, public, all of them should be in there to share and collaborate and communicate. But it's rather easy to share, but as we just saw, there is a report which is